But I believe the Ricci tensor has only 2 indices. Yeah, no, but the Riemann tensor has 4, and you need them. So that is equal to G, say DE times R A B C E. Yeah, he's a little tired. All right. So then there's a lower index. So this is the one we derived. That was our definition. And then it has the symmetries RAB, maybe put that. CD is minus RBA, CD, RAB, CD is equal to minus RAB, DC, and RABCD is equal to RCD AB and RABC D plus RCABD plus RBCAD is equal to 0. Are these all the symmetry relations we can derive? There's one more that involves derivatives. But did this realize how much you can reduce the number of variables, because this is for there are 256 components. Now, that's kind of nasty, honestly. This is symmetric and symmetric in this. So how many combinations are there if this is symmetric? Well, if that is symmetric, so ABCD is the same as BACD. No, in terms of this. So how many independent combinations you have of AB? 4. No, AB. Wait. They can run from one. Each of them can run from 1 to 4. Oh, so you start. So 16. Yeah, but it is symmetric. Oh, 8. No. Oh. You have a symmetric matrix, so you have 4 plus 3 plus 2 plus 1. It's probably something like 10. Then. Oh, right. There are 10. You just can't flip. Like 1, 1, 2, 2, 3, 3, 4. Yeah, and that means for this there are also 10 different ones. So you would think and actually that's when it was symmetric, but it's actually anti-symmetric. So when anti-symmetric, when they are the same, this is not there. So we actually can do better. So it is 6, and there are another 6. So we end up with basically 36. But now we also have this relation, and here it is symmetric. So that means that we have 6 times 5 divided by 2. That is 15 components. And it turns out that this is actually only one relation. So you end up with only 14 components. So that's a lot easier to deal with than something like 256. Yeah, that means we have to calculate a lot less. The Ricci tensor. So these are all tensors, and I want to introduce the Ricci tensor. Where did I write it down? The Ricci tensor is a contraction. So we have, say, RAB. We contract then the first with the third indices. So say that is A, that is C, and this is B. So this one is contracted. So this is the Ricci tensor by definition. So this one is the Ricci tensor, and this one is the Riemann tensor, yeah, with indices C, A, C. And the reason we do that is that we have a tensor with 2 indices. We have another tensor with 2 indices, that's the metric tensor. We still have another tensor with 2 indices, and that is the energy momentum tensor.
Yeah, I see. That's what I wanted to cover for a while now, actually. So you can multiply these together relatively easily, right? 2 by 2 tensors.
Yeah, you could do that, but then you might lose too much information. In equations in physics, if you have a tensor, so the tensor form on the left has to be equal to the tensor form on the right. And so that means that if you want to relate matter, so this is matter, that is energy and momentum tensor. If we would want to relate matter to curvature, the only objects we have are, these are the tensors we have. And for dimensional reasons, we also should multiply this also by the curvature tensor. And maybe I have to call that A prime again. So what can we have for the Einstein equation? The only thing what we can have really is R.
I suppose you can also add all these tensors because they have the same dimensions.
Yeah, so plus alpha GAB times, this is called R, the curvature, is equal to beta times TAB. So this is the only way how curvature can be related to the energy momentum tensor. And that means that the equation that describes gravity, that must be this equation.
Right, and it just takes a little bit of computation to figure out what alpha and beta are.
For alpha is actually, we have one relation which I didn't discuss. That is the so-called Bianchi identity. It's actually quite some work to derive it. That is the covariant derivative of R, B, C. This is anti-symmetrized. What is that? R. BC. I didn't put the bracket. I have to look. It is not in my notes. The identity is R. Now D is not. Let me see. I will write it like this. This D and F is equal to 0. This is the Bianchi identity. And you can derive it. You have to work with how the Riemann tensor is defined. And from this identity, it follows that this alpha is equal to -1/2. So there's no other possibility. That is just determined by the math, because we know that this identity should be valid. And that identity just follows from the commutation relations of the covariant derivative.
Right. And this one, I'm sure Dad can recite it by heart. You know what it is, right?
Yeah.
What is this? Beta?
Beta.
8 pi g. How would you derive this?
This is actually much harder to derive. And you derive it by the weak gravity limit. Because we know the physics for weak gravity. That is just, the gravitational potential is G times m divided by the distance.
Oh, finally, he found something he understands.
This is a weak gravity. And
so that's just classical gravity.
And if this is,
yeah, Professor R squared.
Oh, that's potential.
This is potential. Yeah. So if this is going to describe gravity, so if the gravity is weak, it better describes this. And weak gravity, we know what it means. It means that the metric tensor, say GAB, is very close to the metric tensor of Minkowski with -1, 1, 1, and zeros. That's this one, plus some small addition that is gamma AB. And to derive it, what you have to do is you have to insert this into that expression for the Christoffel symbols and the Riemann tensor and expand to first order in gamma. And there are many terms. We said there were 15 terms. You have to do it for all 15 terms, work them out to first order in gamma, and then you find an equation for gamma, and that reduces to this equation, and but you have to do a number of tricks. You have to do coordinate transformations, because we know that this is valid in all coordinates. We can do that to simplify the equations. And when you work to first order in this, you can simplify it actually more. And you have to choose the right coordinates to rewrite it in a form where you actually can relate it to this equation. So what we know is from a gravitational potential that this is equal to 4 pi g times the matter density. You know that equation? And I have to check the sign. Let me do that. Yeah, exactly. I have to look at. So there are quite a few pages before. It requires a lot, because I'm really many pages on. No, it is already found earlier. And let me see where. Yeah, no, I got it right. 4 pi. So this is called the Poisson equation. It is equivalent to this one. When you think of rho of r as the sum of masses mk times delta r minus rk. So when you have, this is what is the matter density, and these are point masses. If you solve this equation, you find that this is the solution. And you can reduce this equation to this equation. You can kind of see it because these are all second derivatives. And we can simplify it so that it only has these derivatives. And then you find that this is equal to 8 pi g. But that is not a straightforward equation. So you have to work on it. And then we know how it works.
All right. I wouldn't want to focus finding beta, but I actually want to get some intuition about what the energy momentum tensor is before we get into it.
Yeah. So what is the energy momentum tensor? So you know, an energy.
Does it represent like a distribution of mass?
Yeah. So you know, for example, kinetic energy. That is just 1/2 mx dot squared. This is a vector. That's kinetic energy. We also know that this is so these are velocities. So what we have, it is quadratic in the velocity, and in relativity, these are the UAs. That's the force velocity. If you have free particles, that is kind of the only thing we have with this dimension. So what you can do is you can make these combinations, UA, UB. That would be a good tensor made out of velocities. So that is what you can make out of matter. And it has to have some density. So that's the energy momentum tensor. So it are these kind of things. So it includes both energy and momentum. U0 has only a gamma factor. So and UK, the spatial components, that these are the velocities times gamma. So that means the 0b are kind of the momentum. So this is a mass, a typical mass density per unit volume, and so that gives you a mass times a velocity as a momentum, and the 0 component is just the density. That means just the masses, the energy stored in mass. And when both are non-zero, say the diagonal components, UA, UA, that's kind of the kinetic energy. And it is related to the flux of momentum. So how momentum goes through a surface.
I feel like a flux is something for a vector field, right? And not something like momentum, which then.
Yeah, momentum is also a vector. And
but it can be.
So it is something. So for example, if you have a current, you can talk about current density. You can talk about the flux of a current, how much charge goes through a surface. So you have a surface like that. There's a current here, and how much charge flows through this surface. Here, first of all, this is four-dimensional, so it is much harder to imagine. And but this is also related to flux in particular, because there's a conservation law that say dA of TAB is equal to 0. This is the conservation of energy and momentum. And if you integrate this over some volume of dA TAB, and this is a four-dimensional volume, you can integrate this by parts, and then this becomes an integral over the boundary of the four volume. Maybe I do it different first. So what I do is I take the 0 component. So let me do a three-dimensional integral instead. So I have here the 0 component times t0b, and now I do integrate over a three-dimensional integral, so this is v3. And then the second term is integral dA TAB, and these are now spatial components. Summation over, we have AB 1, 2, 3 only, or A1, 2, 3, D3x. So in this integral, this differential can take out, you can take out. So this is then the time derivative of this thing, and if I integrate this by parts, it becomes a two-dimensional surface. That's the boundary of V3 times TAB times a normal with index A times a surface integral.
I'm sure it's somewhat hard to visualize integrating over something four-dimensional.
That's why I changed it to three dimensionals, and because of this, you see that this is something like the momentum contained in this box, and this is the time change of the momentum. What we have here is so this is TAB. So now this is my box. So these are the boundaries of the box. So this is the boundary of V3. I integrate over the boundary. The normal vector is this vector. So these are the normal. So what we do is we project this tensor on the normal, here with a minus sign, and here with a plus sign. And that is why this is the momentum that flows inside the box here and flows outside of the box there. So what it says is that the time change of the momentum is equal to the momentum the difference of the momentum that flows into the box and out of the box. So that is how you basically can interpret this conservation relation.
I see.
So that is what you really mean by the physics. Normally, you don't really think about it that much. You just you know that this is the case, and you use it. But if you want to do real computations, you have to use it. In the Einstein equations, if the derivative of this is equal to 0, and in fact it is in general relativity, that is when g mu nu is not equal to eta mu nu, then this becomes the covariant derivative of A and B is equal to 0. And that means that also in the left-hand side, the covariant derivative must be equal to 0. And that is indeed the case. That is one thing we didn't show yet. We know that we have this identity, but we can always find coordinates where the covariant derivative of the left-hand side is equal to 0. So there are a number of steps missing. That is first prove that this one is equal to 8 pi g. Also to find coordinates where this actually simplifies. And then you use the fact that the covariant derivative of this vanishes.
I guess I want to discuss like a formal, well, is this a formal definition of the energy momentum tensor?
Maybe maybe this is the definition.
Oh, so just the covariant is zero. Covariant.
This is a tensor of which the covariant derivative vanishes, and with the dimension of energy.
And that's not too broad, right?
Because also the covariant derivative of the metric tensor vanishes. But this doesn't have the dimension of energy. Also, the covariant derivative of this vanishes. The definition.
So I suppose that the energy momentum tensor is just a function of energy, such that when you take the covariant derivative, it goes to zero.
Yeah. So what this is, it is really the momentum flux of component A through the surface with normal B.
All right.
But that is even hard to visualize. So the strict definition is in terms of fluxes. But maybe the simple definition is it is something that is conserved. If you there are not that many conserved quantities, and if you have so this is actually I would say the definition. And you can also ask, what is energy?
What is energy?
Yeah, energy is something that's conserved, and with the dimensions of energy. So you also express that in terms of conservation. Yeah, you could write different form, but the most fundamental thing is that it is conserved.
Yeah. Okay.
And
so the energy momentum tensor is just it's just conserved over time.
That's right. It satisfies this relation.
Finally, we figured out the conservation of energy and the conservation of momentum. We got to that.
But you can make things more precise. We don't have really the time for that. Let me see, what else can I do?
I suppose I would fold like the topic or lesson is a little bit longer at this point.
Yeah.